Okay, let's get started. I checked out the remaining slide, this PowerPoint, and figured that we have 10 more slides left this semester. So that means I think we can, this lecture would be the last one this semester. 10 more lecture slide. To refresh your memory, we are talking about reducing average memory access time, right? And the equation looks like this: the hit time plus miss rate multiplied by miss penalty, right? So we are talking about reducing this miss rate by using different cache structure. And we are in the middle of going through one example, right? So this is the different cache structure with the same size, diagram of cache with 8 cache entries, two-way set associative, right? So here you have 2 cache entries in each set. Here, diagram of cache, you have only 1 cache entry in each set, right? So 4-way set associative, you have 1, 2, 3, 4 cache entries in each set, right? And fully associative, only 1 set, right? So we are going through this example, right? Assuming you are executing 5 memory access instructions from this block address. So remember, so with item of cache, you have misses, all misses, right? All 5 misses. And two-way set associative, you have only, you have 4 misses, 1 hit, right? And fully associative, so I need to explain this, right? So here, if you compare two-way set associative with fully associative, the address is CPU generate, right? CPU generate, and so the same, address CPU generate, and here we don't have an index field because we have only 1 set, no choice, right? So we have no choice. That same set is selected all the time, right? So no index field here. So from block address, okay. So tag field. So let's execute these 5 memory read instructions. Okay, starting from the first one. So LW, memory read from block address 0. Then no choice, right? The set is selected all the time. So hit or miss. Miss, right? So at the beginning, all 4 cache entries are invalid, right? So we have cache miss. Cache miss. Then what we have to do? You have to bring in memory block, right? And then record tag information. Tag information, right? 6 zeros and set validity to 1. Okay, so we are done executing first LW instruction. Next, LW instruction from block address 8. So selecting the same set because we have only 1 set, right? So cache hit or miss. Miss, right? So compare this chunk ID against these 4 tags, then no matches, right? So we have cache miss. Then what should be done? Memory block should be placed, right? So we have empty entries. So you don't have to evict that cache entry to memory, right? You can use unused cache entry. So place memory block and record tag information, and valid bit is set to 1. So we are done. Okay. Then next memory read instruction from location 0. Hit or miss. It is cache hit. Why is that? Because this one chunk ID. This chunk ID is equal to this tag information. So we have cache hit, right? So cache is able to provide data directly to CPU. Okay, so we have cache hit. Then next memory read instruction from location 6. Okay, selecting same set, hit or miss. Cache miss, right? So because what? Because chunk ID is different from these two tags, and these twos are invalid. So we have cache miss. What should be done? Read memory block, right, and place into cache entry. Then record this tag information, right? Okay. So and the last memory read instruction from location 8. So location 8, hit or miss. By comparing this one with this, and invalid, right? So we have cache hit because that guy. Okay. Chunk ID is equal to this tag information. So we have cache hit. So two hit. So if you compare direct map cache, two-way set associative, and fully associative, compare the hit count, 0 hit. Here, 1 hit, sorry, and 2 hits. So as you increase associativity, number of hit tend to increase, right? Number of hit tend to increase. But it all depends on the behavior of your program, memory access behavior of your program. But in this example, right? In this particular example, number of hit increases as you increase associativity. So this is a general trend. The computer architect try to examine different cache configuration. Examine different cache configuration and measured miss rate. Okay, and by running many different benchmark programs, they collected this data point and come up with this graph. Okay, so this one, one-way set associative. So essentially direct map cache. Right? So one way. So in a set you have one cache entry. Two-way set associative. You have two cache entries, right? In one set. 8-way set associative, right? In one set, you have 8 different cache entries. So we are talking about same sized cache. This green, 4K byte. Sky blue, 8 kilobyte. And the last one, brown, 512 kilobyte. Okay, talking about same sized cache. So as you increase associativity from direct map cache to 2-way, 4-way, 8-way, so miss rate tends to go down, right? So here 10% miss rate. So here 8% miss rate for 4K byte cache. So here a little bit, right? A little bit better, right? So brown, right? So largest gain can be achieved from dynamic cache to two-way set associative. We can skip. We can skip this, I guess. So which part of the address you can use for indexing the cache and chunk ID, right? So fully associative, you don't have index field, right? Index field, that whole thing is used as a chunk ID. So because we have only one set. Okay, one important thing we have to discuss. Probably this one. This one, Minji, can you please? Minji, can you please? Okay, Minchang.
Can you hear me?
Mm-hmm.
Okay. Replacement policy. Upon a miss, which waste block should be picked for replacement? Direct mapped cache has no choice. Set associative cache prefers non-valid entry if there is one. Otherwise, choose among entries in the set. Least recently used, LRU, choose the one unused for the longest time. Hardware should keep track of when each waste block was used relative to the other blocks in the set. Simple for two-way, takes 1 bit per set. Manageable for four-way, too hard beyond that. And then random gives approximately the same performance as LRU with high associativity cache.
Okay, thanks. Replacement policy. What is that about? If you look at, it's a direct map cache, right? In direct map cache, you have only one. You have one cache entry in each set, right? So like this, right? You select particular. Hold on. Okay. So in direct map cache, if you look at direct map cache, right? You select one set, right, for lookup. Then what if this entry, this cache entry is not containing the data you are looking for? Then you don't have any choice. You have to sacrifice, you have to evict, you have to replace, right? You have to replace this cache entry to memory if it's dirty, right? You have to store this cache entry, cache line to memory and bring in new memory block. So in direct map cache, you don't have any choice, right? Because you have only one cache entry in this set, right? So that is a replacement. We are talking about replacement policy. So in direct map cache, you don't have any choice. You have to replace that particular set because you have only one set, one cache entry. But when it comes to set associative cache, for example, two-way set associative like this, right? So you select, one particular set for lookup, right? For example, set number 2. Assume that you selected set number 2 by using that index. Then you have two cache entries, right? Two cache entries. Then which one do you want to sacrifice? Which one do you want to replace, right? So we're talking about the replacement policy. Probably LRU cache entry. Which one is least recently used, right? LRU. That is, I think, intuitive and natural approach. Then the question is, how do you implement LRU in hardware, right? That should be managed by hardware, right? So in two-way set associative, very simple. You can use just one bit for each set. Okay, so like this, set number 0, you have a LRU bit. Set number 1, you have LRU bit, right? So LRU is, let me draw. So two-way set associative, you have LRU, right? So way number 0, way number 1. So set number 0, set number 1, set number 2, and so on, right? Set number 5, 11, for example, okay? So two-way set associative, it is very simple. You need just one bit, right? One bit LRU, right? So say LRU is 0, this bit is 0, then this one, way 0 contains, the way 0 is LRU, least recently used entry, least recently accessed, okay? Least recently accessed. So you want to replace that guy, okay? You go out, I need to bring in new memory block, right? So LRU. Because we want to use temporal locality, that characteristic in your program, right? Temporal locality. If you access memory location, very likely to access same location again in the near future, right? So recently used, right? You recently used, according to this LRU bit, you recently used that cache entry. So this one is accessed a relatively long time ago compared to this one. So you want to sacrifice this guy. So two-way set associative, probably it is very simple. But what if four-way set associative cache? So let me do like this. Okay, so let me use this space. Okay. Here. Tag data, way number 0, number 1, 2, 3. The question is how many bits? How many bits you need? How many bits? How many bits you need for LRU, for four-way set associative? Let's say set number 02, set number 511, right? So what do you think? So how many bits? How many bits to select least recently used cache entry? What do you think? Yeah, Hemi says 2-bit. Answer is no. Answer is no. Not 2-bit. So why is that? Yeah, that is so 2-bit. Let's say okay. So 2-bit. If you say 2-bit, then 00, right? 00 means okay. That guy is LRU. Okay, so that means probably you think way number 0. So you have to sacrifice, replace that guy. 0, 1, 1, 0, 1, 1. Four different cases you can represent with a 2-bit, right? So that is way number 1, way number 2, and 3, like this, right? So LRU says say 0, 1, then you want to sacrifice this guy. And what is the problem with this 2-bit? Let's say LRU is 0, 1, then you have a cache miss. So you are replacing that guy. Okay, you go out. Okay, you go out. I need to bring in new memory block, right? Then on which one? Which one is next LRU? Which one? This one should be changed to which one? 0, 0, 0, 0, 1, 0, 1, 1, which one? And how do you know? You see the problem, right? So what is the problem? Problem is with the 2-bit, you don't know the history, right? Access history. Which one is accessed most recently used? Which one is most recently accessed, used, or accessed, right? And which one is least recently accessed, LRU? And which one is second most LRU? second, which one is second LRU, second LRU, right? So you don't know the order, the access order. You cannot use 2-bit to encode that history, right? Okay, for example, way number 0. Okay, I accessed, your program accessed way number 0 first, then way number 3, then way number 2, then way number 1. That is access history. Okay, that is LRU, least recently used, and this one is most recently used. So in this case, you have to say 00, right? LRU, but 00 here. But by using this only 2-bit, you don't know which one is second second LRU, right? Least recently used, right? You see the problem, right? Then how many bits you need to implement LRU in Way Set Associative? Anyone? 8-bit. Oh, that is too many. 8-bit, that is too many given. We want to reduce the amount of bit because that is directly related to hardware cost, the price, right? So if you use probably 8-bit, yes, you can use 8-bit to implement LRU, but that will be, that will be expensive, right? So we want to somehow reduce the minimum amount of bit to implement LRU, right? So what would be the minimum amount of a bit to implement LRU? And why? So let me do this. Create LRU bit 4 way set associative cache. First one. Okay, 4 choices. First one. 2-bit is not the answer, so 3-bit. About 4-bit. 5-bit. 6-bit. Okay. LRU. Q. Question. Okay. Launch. Can you answer to this question? Uh, 4-bit. So 50% of you. 50. Okay. Okay. More than half. Okay. 4-bit. So majority of you voted for 4-bit. Okay. Let me finish. Okay. And share the result. You know what? Answer is what? Answer is 5-bit. Answer 5-bit. So why is that? Why is that? So you need to figure out how many different access pattern, access history are present, right? So like this. Remember, I think from high school studied this, I think. Way number 0, way number 0, way number 1, way number 2, and 3. Then 3 other choices. The first one, this one is LRU, least recently used. Then 1, 2, 3. 2, 3, 1, 3, 1, 2. And then 3, 0, 1, 2, 3, 2. 0, 1, 2, 3. 0, 1. Okay. 1, 0, 1, 2. 0, 1. Same thing, right? You can do this, right? 0, 1, 2, 3, and so on, right? You can do the same thing. So that is all the possible, all the different possible access, access history, right? So starting from way number 0, right? So look at this one. So way number 0 first, and way number 1 second, 2, and 3. That is MRU, most recently used. Okay. So then, how many different cases? So 4 multiplied by 3, and 2, and 1, right? Then what is that? 4 factorial, right? 4 factorial. That means what? How many different cases? 24. 24 different possible access history, access pattern, right? Then how many bits you need to implement LRU? 4 bit is not enough, right? 4 bit is not enough, right? Why is that? 4 bit, 2 to the 4. Then 16 different cases. That can cover 16 different cases, okay? But you need 24. So you have to have 5 bit. 5 bit, this one. 32 different cases, right? So you need 5 bit. Okay. And another question is then, okay, I figured out, okay, we need to have 5 bit to implement LRU, but actual design of that LRU is really complicating, right? So how would you design digital logic for LRU? Digital logic design, actual design. Okay, we logically understand we need 5 bit. Then the question is digital logic design, right? So how to design it? Remember finite state machine in digital logic design? Finite state machine. Okay, say this access pattern, okay, access history, let's call this S0. And second, call this S1, okay, state 1. S2, then until S23. So you have 24 different states. Okay, S0, remember? S1, S2, S3, and S23. So you reset the machine, you turn on the computer, and then let's assume you go to S0 state. Okay, then depending on the way you touch, okay, then you can go to many different states, right? Say 0, 1, 2, 3. Okay, so that is MRU. Then you have a cache miss. Then you have to sacrifice this guy, way 0, right? You have to sacrifice this guy. Then bring in new memory block. Okay, then access history will be, okay, you sacrifice this, you just touch it, this guy. So history should be 1, 2, 3, 0, right? 1, 2, 3, 0. I don't know which one. S02. Let's call this as I don't know, S 11. Okay, I don't know. Okay, S11. Okay, S11. So if you have a cache miss, then replaced it, then you should go to S11. Okay. Okay. So you have to draw this finite state machine, then implement FSM into actual digital logic. So it is going to be pretty complex, very complex, digital logic. And the thing is, you have to design that LRU logic for each set number 0, digital logic, right? Digital logic for that set number 0. Another digital logic, okay? Same digital logic for set number 1, okay? And then the last one, set number 511. Okay. So what if you have 8-way set associative cache? What if you have 8-way set associative? Then how many bits you need? 8 factorial, right? 8 factorial. So let me compute. What is that? 8 factorial. 8 factorial. Okay, 40,320 cases, right? Then how many bits you need to implement LRU? Roughly 40,000. How many bits? Roughly 40,000. Then how many bits? 15 bit is not enough, right? 15 bit is not enough. That is 32K, right? Roughly 32, right? So that number, 32,000 roughly, right? So 15 bit is not enough. So you need to have a 16 bit. 16 bit to implement LRU. So that is 64, okay. 64,000, okay. And then, finite state machine, FSM is going to be, that many state, right? So that many state, 40,000 different state you have to draw, okay, from state 0, okay, to go to, depending on access pattern, go to S11, too many, lines, right? So, implementing LRU for 4-way set associative, I wouldn't say it is impossible, but do you want to design it actually? No, right? I don't want to design LRU, right? So here, it is simple for 2-way set associative, probably manageable. For 4-way set associative, but 8-way, I don't want to design it, right? It is too complicated, right? And LRU logic itself is going to be, huge, probably bigger than cache, bigger than this actual cache, right? LRU logic, right? So, LRU, true LRU is not actually, used in the real, processor. Okay. And the real processor, the people use pseudo LRU, simplified LRU, or random. Okay, randomly pick. Okay, random. Okay, so you have cache miss. Then which one do you want to pick? Okay, random. Okay, I want to pick this guy. I want to pick this guy, random. Okay, and if you measure the performance by running many different benchmark programs, you can measure the performance, right? So LRU actually is the best, but the difference between LRU and random is not that big. So random is okay to use. Any question? So if you check out real computer cache configuration, where is that? CPU-Z, okay. The computer, the computer in my office, the one I'm using, right? So look at this. So cache, we'll talk about these multiple levels of caches, but here, take a look at this associativity. 8 way set associative and 16 way set associative cache. Okay. Implementing LRU for 16 way set associative, 16 factorial, right? Then check out this number. How to read this number? I don't know. Billion, trillion, 20 trillion. Is it trillion, right? 2 billion, right? And 20 trillion different cases, right? Do you want to implement that? Okay, no, it is not possible, right? It's impossible. So in actual commercial processor, LRU, true LRU is not actually used. Pseudo LRU or random, right? Random replacement policy. Okay, any question about associativity, different cache configuration? So here to refresh your memory. So we are talking about this, right? We are talking about reducing average memory access time. So why? Because that has a huge impact on computer performance, right? Right? So we just talked about this miss rate. So how to reduce miss rate? So you can reduce miss rate by employing different cache configuration. And there are pros and cons. There are some good things and also bad things, right? Depending on cache configurations. So direct map cache. So you can see this, right? Direct map cache. Then set associative and fully associative. So the first one you can measure is access hit rate, probably hit rate. Miss rate or hit rate? Miss rate. Let me use, okay, miss rate, okay. Miss rate, direct map cache. When it comes to miss rate, fully associative cache is the best, right? It is pretty, small, and miss rate is very high and very low. Okay, so we, went through, example, right? Particular example. And how about access time? Access time or hit time, right? Hit time. That hit time. Access time. Direct map cache is very simple, right? So if you take a look at this one. So direct map cache, you select one particular set. There's only one cache entry. So you read out tag information and data. Okay, tag is equal to chunk ID. Then we have cache hit. That access time. So reading data from the cache. So the cache structure is very simple. So access time is pretty fast. Access time very fast. And this one, fully associative cache, it is very slow in the medium, right? So why is that? Fully set associative cache. Compare that against this one, set associative, four-way set associative, for example. So you select particular set, then 4 cache entries are coming out at the same time. Right? At the same time, then hardware will compare this tag information tag information against chunk ID. So 4 comparators. So one of cache entry is containing the information you are looking for. Then we have a cache hit. Then you have to go through this, multiplexer, bit multiplexer, right? So among these four data, you have to select one. Okay, selection signal is selection signal. You can use hit information. Okay, hit information for selection, right, signal. So you have to go through this big multiplexer. So it is, slow. So if you compare that against this one, so this multiplexer is because we have what? We have a long cache line. This one, 16 byte cache line. Right? So this one is different. This one is different from that multiplexer, right? So for simplicity, I did not draw that multiplexer. So you have to have that multiplexer, right? In for Way Set Associative cache as well, right? You need to have that multiplexer because the cache line size here, we assume a 4 byte cache line, but this is not realistic. No one is using 4 byte cache line. Typical number is what? 64. Intel CPU, right? 64 byte, 64 byte, 64 byte. So you have to select the word you are looking for from this 64 byte. So in this, again, in this schematic diagram, I did not draw that multiplexer. But you need that multiplexer right here. And in four-way set associative, you need additional big multiplexer. So it is taking 32-bit data, select the final one. A pretty big multiplexer. So that is why it is slow, right? So select particular set, then information is coming out. That those information is coming out, then you have to go through, additional memory hardware component. So it is going to be slow. And the last thing you have to consider is hardware cost. Hardware cost, meaning how many hardware cost, how expensive it is. It is cheap because you use less amount of hardware component, AND gate, OR gate, flip-flop, those things, right? And this one is going to be expensive. And expensive. So why is that? Think about, four-way set associative. You need 4 different comparators. 4 different comparators, AND gate, and additional multiplexer. Whereas direct map cache, you have only one way, right? You don't have, way 1, way 2, way 3. You have only one way. You have only one comparator, one AND gate, and so on, right? So it is going to be cheap. You use less amount of hardware resources to implement direct map cache, right? So you have to compare. These 3 different metrics to measure to figure out which one do you want to use in your design, right? So there's a trade-off, right? Any questions so far? Yes, Yunshik. Yes, you are correct. Okay. Okay. Last one I want to talk is this one. So if you go back to the equation, the average memory access time, how to reduce missed penalty. Yunshik, can you please? Q1, can you please?
Reducing cache miss penalty. Use multiple levels of caches. Primary cache attached to CPU, small but fast. Level 2 cache services misses from primary cache, larger, slower, but faster than level 3. Level 3 cache services misses from level 2 caches, largest, slowest, but faster than main memory. Main memory services level 3 cache misses. Advancement in semiconductor technology allows enough room on the die for level 1, level 2, and level 3 caches. Level 2 and level 3 caches are typically unified, meaning that it holds both instructions and data.
Okay, thanks. Reducing miss penalty. How to reduce miss penalty? We can use advancement in semiconductor technology. So the solution is you can use multiple levels of caches like this, level 1, level 2, level 3 caches. And we were able to design this multiple level of caches because of the advancement in semiconductor technology. What does that mean? Advancement, right? The transistor size is getting smaller and smaller. That is the basic unit of designing digital logic, right? Transistor size. So switch size is getting smaller and smaller. So you can integrate more and more transistors on the same size, same space, right? So thanks to the semiconductor technology, we are able to design this multiple level of caches. Okay, one big monolithic cache is not helping. Right? One big, assuming that you have only one. Okay, you don't have L1, L2. You don't have L1, L2. You have assume that you have big monolithic, 8 megabyte, super big, cache. Just one cache. Then that is not the solution. Why? Why is that? The access time, heat time. It takes too long time to access that big cache. Right? That is the problem. So we want to use this multiple level of caches. So first level cache, L1 cache, very small, 32 kilobyte. And then the L3 cache, level 3 cache is pretty big, 8 megabyte cache. Right? So again, thanks to semiconductor technology. Right? So that is a typical configuration. Level 1 caches are separated. This one is holding only instruction. Level 1 instruction cache. This one is holding only data. Level 1 data cache. That means we have separate connection from CPU to level 1. So that is used for instruction patch. And this one for data access. Remember the pipeline execution stage? Patch, decoding, execution, memory access, write back, right? Patch stage, you can use this one. And level 2, level 3 are typically unified, meaning that L2 is holding both instruction and data. Same thing goes to level 3. Okay? So the thing is, our level 1 cache is small. That is why the access time, okay, heat time is going to be very small, very fast heat time. Okay, and if you miss level 1, then you have a backup plan, level 2 cache, right? Level 2 cache can serve you. But if you cannot find the data you are looking for, then another backup plan, right? Level 3 cache, huge, 8 megabyte. If you miss level 3, then you don't have any choice. You have to go out to the memory and access it, right? But we want to reduce main memory access as much as possible, right? That is the one, okay, we want to achieve. And this one is typical block diagram, actually, Core i7. The first generation of Core i7 called the Nihalem. So you have 4 CPUs, 4 cores, Okay, 4 CPUs, 4 cores. Then big level 3 cache. Okay, this level 3 cache. This one is called also last level cache, LLC. Okay, the L3 cache, L3. So L3 cache is LLC in that hardware configuration, right? Level 3 cache, last level cache. And level 1, level 2 are private cache. Private. Okay, level 1, level 2 are integrated inside this core. Okay, it is only serving level 1, level 2. These two are serving only this core, this CPU. Same thing goes to here, right? This L1, L2. These guys are serving only this core number 3, this core. Okay, but level 3 cache is also shared cache, unified and shared cache. Shared meaning 4 CPUs. Okay? It is serving 4 CPUs, shared cache. So private cache, private and shared. Okay. Okay. Okay, let's skip this part. Skip this part. And the last thing I want to discuss. This one. Hemin, can you please?
Can you hear me?
Mm-hmm.
Multi-level cache design considerations. AMAT equals hit time plus miss rate times miss penalty. Design considerations for L1 and L2 caches are very different. L1 should focus on minimizing hit time in support of a shorter clock cycle. L1 is smaller or faster, but have higher miss rate. L2, L3 should focus on reducing miss rate and reducing L1 miss penalty. High associativity and large cache size. For the L2, L3 cache, hit time is less important than miss rate. Miss penalty of L1 cache is significantly reduced by the presence of L2 and L3 caches.
Okay, thanks. So the last thing I want to discuss is this one. For level 1 cache, what kind of cache configuration you want to use? Do you want to use direct map cache, or set associative cache, or fully associative cache? How about level 3 cache, DM cache, SA, fully associative? Which one do you want to use? So based on that equation, think about that. Based on that equation. Okay. So think about level 1 cache first. Level 1 cache, which one do you want to use? Which one do you want to use? Direct map cache, set associative, fully associative? Which one for level 1? There are 3 factors you have to consider. So there are 3 factors, right? Miss rate, access time, hardware cost, right? If you use direct map cache, miss rate is very high. Okay, very likely to miss. Then you have to. That means you have to go out to level 2. Level 2 can serve you. If you miss level 3, level 3 can serve you. Okay, something like this. And access time, super fast, very fast access time. Okay, if you use direct map cache. Okay, and hardware cost, it is cheap. Right? But you can ignore this part. Because transistor is getting smaller and smaller. So you can integrate many different transistors. Okay, you can just ignore this part. So consider these 2 factors, miss rate and access time. Which one would be more important? Which one would be more important for a level 1 cache? If you look at this equation, for level 1 cache, hit time would be very important. T time, right? This time, access time, this time. You want to serve CPU fast, right? You want to supply instruction and data fast. That is most important factor for level 1 cache. Okay, so probably you want to use direct map cache or some low associativity, low associative cache, right? Set associative, but some low associative around that cache configuration. Okay? So the thing is this, right? Let's say direct map cache. If you use direct map cache, access time is 1 cycle. Access time is 1 cycle. Then, okay, so what if I increase associativity? How about two-way set associative cache? If you increase DM, if you increase direct map cache to two-way set associative, two-way, then measure the access time, still 1 clock cycle. Then, okay, why not use two-way set associative cache? Because access time is the same, right? Then, okay, let me increase some more. 4-way set associative cache for level 1. The access time, still 1 clock cycle? The delay is still 1 clock cycle? If it is yes, then better to use 4-way set associative because miss rate, right? Miss rate goes down. Miss rate goes down, right? So again, the design choice for level 1 is the first thing you have to consider is access time, right? Because you want to serve CPU fast. So you want to use direct map cache, but the disadvantage of using direct map cache is the miss rate is pretty high. So you want to use the set associative cache with the low associativity. Okay, so you can increase associativity, then figure out this access time, right? And then how about the last level cache? Which one would be important if you juggling these two, right? Miss rate and access time. Okay, juggling, right? Which one would be important for level 3? Access time or miss rate for level 3? How about access time, right? Access time, it is big cache, super big cache, 8 megabyte. That means it is already very slow, right? Even though you employ direct map cache. Access time, big cache, then access time is already very slow, something like 30 clock cycles, even though you use direct map cache. So you increase associativity to 16 way, then clock cycle, access time is 31 1. That is okay. It is not a big deal. 30 clock cycle to 31. One more clock cycle, that is okay. But if you miss the cache, if you miss level 3, then that is going to be a disaster, right? You have to go out to main memory and access it, right? So we want to avoid that situation, right? We don't want to access main memory, right, as much as possible. So the important factor you have to consider for last level cache is miss rate. Miss rate, right? Because again, access time is already slow access, the big cache, right? So access time is increased from 30 clock cycle to 31 clock cycle. That is not a big deal, right? Does it make sense? So computer architect, right? And Intel, AMD, ARM, they are doing that. They are juggling, these different factors, and also run many different benchmark programs to figure out which cache structure, which one would be best for level 1, level 2, and level 3. Okay? They are changing associativity, okay? And run benchmark programs and measure the performance, computer performance, right? Okay, this is a real number. Okay, Intel Nehalem, first Core i7, and AMD Barcelona. Okay, so level 1, 2, 3. Look at this. Probably by now you understand all different terminologies right here. Split instruction cache and data cache. Split, right? Separated, right? And then 64 byte, okay? 64 byte cache line, okay? And associativity. 4-way set associative for instruction cache and 8-way set associative cache for data cache. Associative for the data cache. And replacement policy, tilde pseudo LRU, okay? And write back, right allocation policy, right? I explained to you, right? Level 2 cache. Unified, meaning holding both instruction and data, unified, okay? And associativity, 8-way, okay? And policy, okay? And level 3 cache. Look at this, associativity, 4-way, 8-way, 16-way. AMD Barcelona, right? 2-way for level 1, 16-way, 32-way. Right? Associativity gets increased, right, as you move down, right? Okay, this one, one last thing. Okay, probably this one is more important. Okay, Min-chang, can you please?
Can you hear me?
Mm-hmm.
Okay. Software techniques. Misses occur if sequentially accessed array elements come from different cache lines. To avoid the cache misses, try to exploit the cache structure in programming to reduce the miss rate. Code optimizations, no hardware change. Rely on programmers or compilers. Loop interchange. In nested loops, outer loop becomes inner loop and vice versa. Loop blocking. Partition large array into smaller blocks, thus fitting the accessed array elements into cache size. Enhance the reuse of cache blocks.
Okay, how do your people at Intel, AMD, ARM, they are doing their best to provide, the CPU and the computer, right? Better computer to you, right? But hardware alone cannot do much to increase the performance. So you have to use those hardware resources very efficiently. Otherwise, the performance of your program wouldn't be that good. Okay? See the point? Your program, right? Software should utilize those hardware resources very efficiently. Otherwise, performance is going to be very bad, right? This is a good example. Let me show you. One good example. I prepared two, but first one only, right? This one is more intuitive. Loop interchange. In C, if you declare two-dimensional array like this, two-dimensional array, right? Int A 10 and 8, 10, 8, right? 10 different row X, right? Confusing, right? 10. So A00. So first element, right? A0, 0, 0, 1, okay? 0, 0, 7, right? The first row, right? Row number 0, row number 1, right? Row, right? Row number 9, 10 different rows, right? And 8 different columns, right? So two-dimensional array. If you declare a two-dimensional array like this, local variable, And C is using row major ordering, meaning that that array is stored in memory like this. Okay, so look at this, right? The data, 8 data is 8 data in the first row. Okay, 8 data in first row are stored in consecutive memory locations like this. 8 data in consecutive memory locations. And next 8 data, okay, next 8 data, this one, okay. Row number 1, that is also, those are stored in consecutive memory locations. Okay, so that is a row major ordering. Okay, and look at this code snippet. This code is simple, right? You want to add all the element in two-dimensional array, right? Simple code. Then you use two, for loops, the outer loop and inner loop. Outer loop you are fixing, right? I is 0. Then you are fixing what? Row, fixing row, and increase these columns, right? So inner loop is increasing columns. J is equal to 0 to n. Right? So what if you write this code? Look at this. Let me show you two different versions of the code, right? So this is us doing some operation. And here you are, J is what? You are fixing column, right? You are fixing column, okay, column. Then increase row, right? Increase row, I 0 to 5,000, right? Increase row. Then the access pattern would be like this. Your program is accessing the data in array like this, right? But if you change this one, if you interchange, if you switch inner loop to outer loop, right? Then you are fixing row, then change this column, right? Like this, right? Then access pattern would be access pattern looks like this, right? Data access pattern, right? You see the problem? What would happen in this case? If you write this code, then in the worst case, every time you access element in two-dimensional array, you have cache miss. So if you go back, access pattern, right? The first code, this code, okay, this code, right? You are accessing first element and for the element in the first row, and you are accessing element in the second row and third row and so on, right? So check out this. You are accessing A00, then A10, A20, and so on. That is access pattern, right? Of the first code. But if you write this code, the access pattern, you are accessing like this. Okay, A00, A01, A02. So when you access A00, you have cache miss, right? Then whole memory block. In this case, memory block size, cache line size, 8 words, right? So cache will store this whole memory block into the cache. So first time you access the data, cache miss. But second data cache hit. Third one, cache hit, right? So you would have many cache hit. Whereas first code, you have cache misses, right? So you can measure. Actually, you can test that code with your computer, right? This code. So here, so I declared, I created a two-dimensional array. Array size 1024, row 1024, columns. Right? I declared using dynamic memory allocation. Dynamic memory allocation, I created two-dimensional array of this size. Okay, and then initialize it. Initialize all the element. Okay, here, and then simply add everything. Simply add to everything, all the element in this two-dimensional array, and I'm looping this. Okay, I'm looping this 1,000 times. Okay, and print out the outcome. So if you use that utility program called perp, okay, then you can measure some detailed information behind that program execution, like how many cache misses. Okay? So let me show you. So here, demo program loop interchange. Look at this. So here, bigger array, two-dimensional array, 2048. Actually, 2048 by 2048. And created it, initialized it, and simply add it, right? 1,000 times, right? So this code, look at this one. This one, look at this. You are fixing I, right? I. That means row is fixed. Then your inner loop is incrementing columns, right? J0 to M. Okay, incrementing column. It is cache-friendly code, right? Cache-friendly. Let me compile it and execute it on this machine. GCC loop interchange. Compiled it and execute it, right? Loop. You just execute it, then okay, you see the result, right? But you want to measure the execution time, some detailed event like cache misses. How to measure? You can use program called perp. Okay, it's perp performance, right? And list. You can measure. Okay, perp list. Then you can measure many different metrics like L1 data cache miss, last level cache store miss, last level cache load miss. And you can also measure how many instructions got executed to run that program, right? And how many clock cycles were used to execute that program, right? So it can measure, it can report many different useful information to you. So the command looks like this. Perp, I did that because history. Okay, this one. So here, look at this. I want to event -e. Okay, report CPU clock cycles. How many clock cycles to execute that program, right? Event instructions. How many instructions got executed? Okay. Also report last level cache, read miss, right? Load miss. Last level cache, right? Read miss. Okay. So you are executing LW instruction, then miss cache, then that will be counted here. And event store misses. Okay, store misses, last level cache. And finally executable, loop interchange. Let me execute it. Okay, it says this. It took 6.6 seconds. Okay, it took 6.6 seconds CPU cycles. How to read? 27 billion clock cycles, right? Roughly 27 billion clock cycles. And 63 billion instructions, right? To run your program, right? And then how many misses? 8 million load misses, 8 million read misses, right? And roughly 700,000 store misses, okay, for that program. So let me simply change. Let me make it cache unfriendly code like this. I simply switch it, these two. Here, J is fixed, meaning column is fixed. And inner loop, right? Inner loop is incrementing row. So it is cache unfriendly code, okay? So store it and compile it, GCC, and run the same program, right? Superb. It takes longer, right? Okay, look at this, compare this, right? Compare this, 22 seconds versus 6 seconds. And look at this, check out load misses. Here, 8 million read misses, but here, 258 million, right? 258 million misses, 8 million, 258. Okay, that is why execution time is pretty long compared to this one, because you have so many misses, right? Here, now look at this. Number of instructions, roughly the same, 63 billion instructions here, 63 billion instructions, roughly same, right? Same number of instructions. CPU cycles, 92 billion clock cycles. Cache unfriendly code, 27 billion, 92 versus 27. Okay, so on average, each clock cycle, CPU were able to execute 2.3 instructions per clock cycles. Cache friendly code, and versus this number 0.68 instructions per clock cycles. Okay, so probably you are curious, how come each clock cycle each clock cycle, can you execute more than one instruction? 2.3? How come? Yes, because Intel CPU x86, it is superscalar, not scalar CPU like the one we discussed in this course, scalar. Right? Scalar, you are supplying CPU read, one instruction, just one instruction from memory and execute it. But superscalar, CPU read, for example, 4 instructions at the same time and execute it. That means you have 4 different pipelines in Intel CPU. That is why this number is making sense. Each clock cycle, you can execute more than one instructions. Okay. Okay, so I guess that is everything I have for this semester. If we recap, we spent a lot of time talking about CPU, right? CPU. And before we talk about CPU, we studied the instructions, right? So without understanding instructions, it doesn't make sense to discuss, CPU microarchitecture, right? You should understand instructions first in detail. Then you are able to design, CPU, right? And we spent so many weeks, right? And then probably 5 weeks we spent on that memory hierarchy, right? So this semester, we were pretty slow, right? For some reason. And we didn't have time to talk about this very important hardware component inside the processor called TLB, okay? So, computer, right? Computer system or computer is composed of what? CPU, memory, and IO devices. So this class, this course mainly focused on only these two, CPU and memory hierarchy. Right? We haven't discussed about this IO component. Also, TLB, we should have talked about this TLB, but we didn't have time, right? TLB. So, but this course is very important in a sense that you understand how your program gets executed inside the processor, inside the CPU, right? But to completely understand computer and computer systems, you should know IO devices, also interaction between IO devices and CPU, like interrupt. Okay, and also TLB, that is missing part. Okay, but we didn't have time. So next semester I'm offering a class called Computer Systems Design. Okay, so you guys are eligible to take that course where we are going to talk about IO devices and interaction between CPU and IO devices, interrupt, exception, okay, using, by going through some example programs, and TLB, okay, virtual memory, the page table creation, okay. So if you are interested, probably you want to take that. I strongly encourage you to take that course, Computer System Design. All right, that is for this semester. Thank you for taking my course. I'll see you around. Okay, anything you want to say? Okay, thanks. I'll see you on Monday. Okay, bye. Thanks.